video. This is on reaction mechanisms. You should have a packet that looks similar to this. We will be filling this packet out. Okay, so our first thing to discuss is, well, what is a mechanism? What is a reaction mechanism? The mechanism is just the process by which a reaction occurs. So you can kind of think of it like a series of steps, except that sometimes these reactions are only one step, meaning something collides with something else and you have products, or it can be a multi-step, meaning there's 2 steps or even 3 steps before we get to the products. So we can have single-step reactions or multi-step reactions. Okay, so now we're on our heading that says elementary reactions. So that's kind of like a vocab word. So an elementary reaction is defined as a reaction that occurs in one step. So it's not a series of steps, it's just one step. So for example, this is an elementary reaction. Because it occurs in one step. This reaction occurs when this NO collides with an O3 and produces the 2 products. Now, just from looking at a reaction, it's impossible to tell if it's a one-step reaction or if it's a multi-step reaction. So you might have that question, like how am I supposed to know? You really don't. A problem would have to tell you, or you would have more information. But so just by looking at something like this, there's no way to tell that it's an elementary or one-step reaction. Okay, so when we have elementary reactions, we can talk about something called molecularity. It's kind of a strange word. So the molecularity of a reaction is the number of reactant molecules that participate in an elementary reaction or in a one-step reaction. So number of reactant molecules. So we have a few choices as to what the molecularity can be, and that's the last thing we're going to talk about in this section. So I'm afraid I'm out of room, so I will move this for you. Okay, there are pretty much 3 classifications of molecularity, and it's all about how many reactants are colliding. So if you have one reactant, that's called a unimolecular reaction. If you think of like a unicycle, has one wheel, right? Means one. So this would be something like, reactant A makes products. Okay, that's a unimolecular reaction because there's just one thing, A. Then we can have something that's 2 reactants, which you might guess is called a bimolecular. And technically we could have 2 different kinds of bimolecular reactions. We might have something like this, A plus B yielding products. Okay, where A and B obviously are my 2. But maybe we have something like this, A like an A plus A or like a 2A scenario yields products, because that's still 2 reactants. So both of those would still be bimolecular, 2 reactants. And then of course we can have 3. You might think it's tri. It's actually not. It's a ter-molecular, almost like inter, but without the in part. So of course a ter-molecular reaction could be lots of things. It might be A plus B plus C yields products. It could be something like 2A plus B yields products. It could even be, 3A yields products. But those, all 3 of those would be a ter-molecular reaction because there are 3 reactants. So that's molecularity. It's just how many reactant molecules you have in an elementary reaction. Anything more than 3 reactants would be a pretty rare thing, and so we don't really have a classification for that, because more than 3 reactant molecules is really something that's not going to happen in a one-step reaction. It would be a multi-step reaction, which brings us to our next heading of multi-step mechanisms. Okay, so multi-step reactions are reactions that occur in more than one step. Multi-step reactions are reactions that occur in more than one step, and they are a series of elementary reactions combined together. So let's say you had this reaction. NO2 plus CO yields NO plus CO2. Okay. If that was my reaction, just looking at it, again, no way to know if it's elementary or multi-step. But then if I told you that it proceeds via a 2-step mechanism, that first, there are 2 NO2 molecules that collide, and that forms an NO3 and an NO. And then in the second step, that NO3 reacts with a CO to produce an NO2 plus a CO2. Now you might be thinking, well, how does this step and this step react together to give this step? Well, actually, this is very similar to when we did Hess's law in the thermochem chapter. And multi-step reactions say that the elementary reactions have to add up to give you the overall reaction. So if you look at this and you use the same idea that we use in Hess's law, that this guy and this guy cancel because they're on opposite sides, and then this one and this one would cancel because they're on opposite sides, look what you have left. An NO2, a CO, an NO, and a CO2, and that matches this. So this is a possible mechanism for this reaction, that it's quite possible that it proceeds in 2 steps. Now, I want to talk about NO3 and what happened with him. Okay, NO3 is special in this case. He has a special name. Let me see. I'm gonna go up top. I'm afraid it's gonna be too low on here. Okay, so NO3 is neither a reactant or a product in the overall reaction. right? Obviously NO3 is not anywhere here, nor is it anywhere here. And it was produced and then consumed in this series of reactions. What we mean by that is that NO3 was made in this first step, and then NO3 was used in this second step, and that gives NO3 a very special name, and that name is that NO3 is known as an intermediate. Okay, so an intermediate is anything that is not in the overall reaction, and it's made, and then it is consumed later on. So NO3 is the intermediate in this case. Multi-step reactions are going to always involve at least one intermediate. There could be two, depending on the situation. If you flip to your next page, there's a practice problem. So take a minute and answer that. I will clean this off and then give you the answer. Okay, this is a pretty easy question. Letter A says, describe the molecularity of each elementary reaction in this mechanism. So that means this first reaction, it wants you to tell what kind of molecularity it has. Well, since it's got one reactant, that's a unimolecular. And the second reaction has 1, 2 reactants, and so that is a bimolecular reaction. B wants you to write the equation for the overall. So again, use Hess's law, a Hess's law-like idea to add these up, see if anything cancels. This O cancels with this O. And over here you have 2 O3s. And notice you have 1 O2, 2 O2, so you have 3 O2s. Everything balances out, and this is your overall reaction. 2 O3 yielding 3 O2. And your paper says D. I guess that should be a C. Identify the intermediates. And so in this case, there's only one, and the intermediate is the thing that is consumed. Produced and then consumed, and that would be the single O is your intermediate in this case. Okay. All right, onward. Rate laws for elementary reactions. Okay, so now we know elementary reactions are one-step reactions. They're very significant for us, and they're very significant because we actually know something about the rate law if we know a reaction is elementary. Elementary reactions are so significant because if we know a reaction is elementary, then actually we know their rate law, and it's because the rate law is based purely on the stoichiometry. So see, I've been kind of lying to you a little bit in that I've said before that you can't use stoichiometry to predict rate law, and that's true for the most part. However, that's untrue in this case. if you know a reaction is elementary, then you can use its stoichiometry to write the rate law, and it works like this. So let's say you encounter an equation that looks something like this. That's a bad example. Let's change it to this. So let's say you happen upon this reaction and they tell you that this reaction is an elementary reaction. Now, they would have to tell you that in order for you to be able to do this. If that's true, then the stoichiometry of this becomes your reaction orders and you automatically know the rate law. And so this is so easy in that we wouldn't have to do any work. We would know that A would be raised to the second power and B would be raised to the first power. But again, that's only if you're told that it's an elementary reaction. Absolutely only if you know. So if you're questioning, if you see a reaction and they don't give you any information on its elementary status, then you cannot use this. It's only if you 100% know that a reaction is elementary. You can cheat this and use your stoichiometry to write a rate law. So again, only if you know its elementary status. So at the bottom of this paper, there's a little chart, and it gives you a handful of elementary reactions, and it wants you to write a rate law in the box. So this is very simple. It's based purely on the stoichiometry, so go ahead and do that. Okay, so there they are for that chart at the bottom of your page, based purely on the stoichiometry. Those would be your rate laws because we knew they were elementary reactions, and so we could use the balanced equation to write the rate law. And that's it for that.